Okay, this video we're going to go through chapter 10, lesson 1, which is preparing to estimate a population mean. And so in this, we're looking at a t-distribution instead of a normal distribution. And so it goes through kind of the difference between the two, and then we're just calculating two different parts of the confidence interval instead of doing the whole thing, because this is that preparing section. So what we'll go through is how to find the value for t star, again, not z star, because we're talking about a t-distribution instead of normal. And then we'll also talk about how to calculate this value, which we'll learn is the standard error. So in a t-distribution, there's more area in the tails from a standard normal. So the standard normal is the orange distribution here. And then they show you one with 2 degrees of freedom is the orange, and then the green is 9 degrees of freedom, just so you can kind of see the difference between the area. So it looks like the lower the value for the degrees of freedom, the more area you have at the tails. So it's still symmetric and unimodal the way that a normal distribution is. It does look like the standard normal, but it has that more area in the tails. So because of this, t star will be greater than z star for any confidence level. We determine this value using degrees of freedom. So degrees of freedom is calculating using n minus 1. However, on the t-table, one thing to notice is that degrees of freedom only go by ones until you hit 30. After 30, it's going by tens, and it even skips 90, and then from 100, it jumps to 1,000. So if the degree of freedom for your problem is not on the t-table, then you're always going to round down. So we'll show an example of this when we get to example 2. So as n gets bigger, it approaches standard normal. So if you look at this last row, it's the infinity values. Those were our z star values. So notice that if degrees of freedom is 1,000, these values are very close to the z star values that we were using in the previous unit. So if I'm looking for t star for a 95% confidence interval, for the population mean based on a random sample of 28 observations, I'm going to calculate degree of freedom by doing 1 minus n, which is 28, and that gives us a value of 27. So I'm looking for 27 here and 95. So if I look at where 27 meets 95, that's going to give me, oops, I didn't change colors. Hold on. That's going to give me a value for t star of 2.052. Okay. So in the next problem, then, if I want a 90% confidence interval, so I'm going to be looking at this column here, for the population mean based on a random sample of n equals 40 observations, my degrees of freedom is going to be 1 minus 40. I don't know why I'm writing that backwards. It's 20 minus 1 and 40 minus 1. Sorry about that. That's going to give me degree of freedom of 39. But again, 39 is not on that table. And so that means that we're looking for the closest value rounded down is going to be 30. Okay, so that means that we're looking at 1 point, oops, not z star, so t star, then for a sample of 40 is going to be 1.697. Okay, so that's the first step in preparing. We're looking at how I use the t-table to find these values for t star. So for the confidence interval to be valid, the conditions for inference must be met. Most of our conditions are the same. They just might be worded a little bit differently. So we're starting with they must be random. So the data must come from a random sample. That's what we're used to. 10% if the sample selected without replacement, and must be less than 10% of the size of the population. And then the last one, which is a little bit different from before, is that it needs to be either normal, approximately normal, or be a large sample. So approximately normal or normally distributed should be described in the problem, or the sample size needs to be greater than or equal to 30. Or we can look at the shape of the graph. So if we're looking for a graph that is pretty symmetric and unimodal, then it's going to look approximately normal. Okay, so we're looking for the graph in that situation. So for example 3 and 4, we're going to use those steps. For 4, we're going to go a little bit further and calculate something else. So the owner of a smartwatch would like to estimate the mean number of steps they take per day. To do so, they select a random sample of 30 days. So remember that when we're talking about normality, that means n is greater than or equal to 30, or we see something about it being approximately normal. So that sample size means that that condition is met. So this is not the correct answer. We also have that word random sample. So random condition is met. So that is not the correct answer. They're going to record, the number of steps they took each of those days. So what we have to check is 10%. So we talked about before that if they don't give me a population, then I probably don't have to check it. But in this case, they're not giving me a population. However, they're talking about number of days. So what we do know is that there are 365 days in a year. And so if I'm looking at the year's data, I know my population. So to check 10%, I'm going to divide my sample size, which was 30. So I've got n equals 30. And I'm going to divide that by my population. So 30 divided by 365 gives us 0.08. Remember, that has to be less than 10%, which is 0.10. So it does meet that condition. So that means that all 3 conditions for inference are met. Okay, so that is a situation where they don't give us the population, but we can check it to figure out if it meets our 10% requirement. For the last example, we're going to look at calculating the standard error of the mean. So if I'm given a situation, I can look at the data and determine if I'm allowed to calculate standard error. So I've got just a screenshot of the Desmos input just to save some time for this video. So in this example, a farmer would like to estimate the mean amount of milk produced per day by his 300 cows. So that's what we're estimating. That's our population proportion that we're estimating. Sorry, population mean that we're estimating. He selects a random sample of 15 cows and records the amount of milk produced in gallons by those cows. The dot plot shows the data. So remember, we're looking for, does it meet the random requirement? So he selects a random sample. It does. Does it meet the 10% condition? So we're looking at is 15 at least 10%, or sorry, at most 10% of 300. So if I divide 15 by 300, that's actually 5%, so that's good. And then last but not least, we're checking normal. So n is less than 30, whoops. And I don't see anywhere that it says anything about normality, but I can check the shape. So if I look at this, it doesn't seem to have outliers. It doesn't seem to be skewed. It has just that one dot, right? The 31's a little bit off, but everything else is beautifully symmetric. So I'm going to say that this is approximately normal based on the shape of the graph. And so that means that I'm going to account that it's good. So to calculate the standard error, we're going to take the standard deviation of the sample divided by the square root of the sample size. So sample size we already talked about is 15. So we're going to divide something by the square root of 15. The way that we're going to do this is we're going to input our list into Desmos. So we had a dot plot. So our numbers were 20, 21, 22, 23, 24, 24, 25, 25, 25, and so on. So I've already inputted those as a set. So I put capital X equals, I put a straight bracket, then I listed those numbers. I just typed the number, then a comma until I had all my numbers. So I had 14 elements. You can double check that there are 14 dots. So then to get standard deviation, what I did is I went to the keyboard and hit functions. From functions, I had to pick stats, and then I chose standard deviation, not standard deviation P, that's population standard deviation. We want sample standard deviation. So that's one without the P at the end. Okay, so when I type that in and then I put the X, it's telling me that I want those values, their standard deviation. It gives us this number. I'm just going to go 3 decimals. So I'm going to use 3.063 as my standard deviation of my sample. So I'm going to put that number here, 3.063. I'm going to use that to calculate the standard error. So that gives me a value for standard error as 0.791. Remember that this is in gallons, and so my units are gallons here. So what does that mean in the context of the problem? So standard error tells us the variation of our sample mean from the population mean. So what is the interpretation of the standard error of the mean? If we select many random samples of milk produced per day by his cows, the sample mean of the amount of milk produced in gallons per day will typically vary by about 0.791 gallons from the population mean. Okay, so the bold statements are the ones that will change based on what your problem says, right? And then obviously what I plugged in, because that was the answer from the previous problem. Okay, so these are just basic steps within learning how to calculate the confidence interval for population means instead of proportions. So in the next unit, we'll actually go through the whole process of finding, or sorry, the next lesson of finding that whole interval.